The topic of discussion in this class is kinematic equations by graphical method. You remember some time back we had considered the particle's motion along the x-axis. Suppose this is the origin and this is my plus x direction. I had taken a small block which could be treated as a particle and I had investigated its motion along the x-axis. At time t is equal to 0 the particle started. Its x coordinate was say x0. At a later time t, at the end of the trip, the x coordinate of the particle became x. Initial velocity was u, final velocity was v. The motion took place at constant acceleration a, say, and this was of course the displacement of the particle from the initial to the final position, right? We had seen that time from the definitions of displacement, velocity, acceleration, etc., that v is given by u plus at. Then delta x, the displacement, is given by ut plus half at square, and v square is equal to u square plus twice a into delta x. These were the three main equations of kinematic equations we have derived that time, in addition to some other equations. We shall see if we can reach there by the graphical method. Now, what is graphical method? We also took some session under the headline Graphical Analysis of Rectilinear Motion. We have seen there that for such a particle moving in a straight line like in x-axis, if we could have the position versus time graph, and then by drawing tangents to the curve at different points and finding its slope, I could find the velocity of the particle at different instants. And then similarly, if I had been given a velocity time graph, say, then again by drawing tangents and finding slope at different points, I could find out the slope from that, the acceleration of the particle. In the reverse process, if I was given, say, the acceleration versus time graph for a particle, say anything, I'm just arbitrary drawing, then the area under the graph, yes, the area under the graph, and that gives me the velocity change of the particle. And similarly again, if I had got a velocity versus time graph, any shape I could have taken, the area under the graph would have given me the displacement of the particle. So you see, the first two had shown how to get velocity from finding the slope of the tangent drawn to the curve in xt diagram, and then again from vt diagram the tangent slope giving me the acceleration. In the reverse process we have learnt the area under the acceleration time graph giving change in velocity, and the area under the vt graph gives me the displacement. We shall use some of these lessons which you have learnt earlier to see if we can arrive at these equations by graphical method. That is the session today. So to derive the kinematic equations, I shall choose the velocity time graph for the particle moving along the x-axis. Let's have a quick look at the figure of the body moving along the x-axis. This was the origin. This was my plus x-axis. The particle in the shape of a small block, say, this is at time t is equal to 0. Its velocity was u, and acceleration remained constant throughout. At a later time t, the particle reaches here. This is the time was t, and the velocity was v. So we are planning to just draw this v versus t diagram of the particle here moving along the x-axis. This is my t-axis, plotting t along this line, and the vertical axis is my position, velocity of the particle as a function of time. And since you can see here that v is changing from u to v in a linear fashion, acceleration remaining constant, the graph, we have drawn it earlier for you, the graph is a straight line. This is the v versus t diagram for a particle moving with constant a along the x-axis. So looking back at the figure, you can see this is the starting point. Suppose this point I say P here, and this is the end point Q. So similarly in the figure, this point P is implying the beginning of the motion, where you can see that time was 0 and velocity was u. This is a scalar quantities, we can treat them as, because the motion takes place along a straight line. Okay, so here the coordinates of P is coming out to be t is 0 here, and velocity of v is u here, right? The last point of the motion, the end point of the trip, is q, where you can see time is t and velocity is v. So here the coordinates should be t comma v. Let's understand this even better with dropping to perpendiculars. As you can see here, I'm doing it if I could drop perpendiculars onto the t-axis and v-axis respectively, I know that this point coordinate is t is equal to t, and here where I have dropped perpendicular on the v-axis, the value of v here is v. This is the meaning of coordinates having t comma v. So this PQ is a straight line, and I'll say that if you remember what we have done before about VT diagrams in the graphical analysis, let me put that here. This was a more complicated figure where we found that the particle having a variable acceleration. So the v versus t graph of the particle was not a straight line but a curve. And at any given instant, if we wanted to find acceleration at any given instant, we had to draw a tangent to the curve, and the slope of this tangent or the slope of the curve, whatever way you call it, that gives acceleration at that instant. The situation is much simpler here because since a is a constant, the graph is a straight line, and for a straight line there is no need for drawing tangents. The slope of this straight line itself will represent dv dt or acceleration. Let me write it here. For this line, the slope of this line itself will be giving me dv dt, that is first derivative of v with respect to time, that is called acceleration. Now how do you find that? What we can do is that we might extend this line backwards, and also the t-axis I could just extend backwards and let them meet here. And the meaning of slope is this, that if this angle subtended by this graph PQ with the t-axis, angle measured anti-clockwise is theta, then this m, slope of this line is given by tan theta, and that must represent dv dt in calculus language, derivative of v with respect to time, and that is the acceleration that is constant in my case, right? So let me do a small construction here. What I'm doing is this, that I'm just dropping a line from P parallel to the t-axis like this, you can see, and similarly I am just dropping a perpendicular from Q onto this line drawn just now, right? This is there. Okay. Now what we do is that the foot of the perpendicular drawn from Q onto the t-axis, let me call that point as R, and here the line that we call PS, right? This is the line PS, this is a perpendicular, this is also a perpendicular, 90 degree each of them. Now you can see here in this triangle PQS, in the triangle PQS, we can see the angle QPS is also theta because the corresponding angle, right? So if this angle was theta, since this t-axis and PS are parallel, this also be the theta angle. And so in this triangle PQS, I could write down tan theta is given by perpendicular, that is the length QS, by base, that is PS. Now what is QS here? Look here, QS. The QS must be given by the whole length QR. Write down the acceleration is given by V minus U by T, and from there we get the first important kinematic equation, that is V is equal to U plus AT. This is my well-known kinematic equation, but we got that in this case by graphical method, interpreting the fact that the slope of this V versus T straight line graph is nothing but acceleration, and eventually reaching here. So keep this first result in mind, and you see here one thing I want you to remember for some time now in the derivation, that this length QS that will be coming again, and this QS is coming out to be V minus U because QS is given by QR minus SR. The whole height QR is of course V, and the height SR is equal to U, so QS coming out to be V minus U. And the length PS that represents time t, and that's equation number 1 could tell me that t can be written to be V minus U by A. We shall need them in a short time during deriving the other two equations.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.